occurrence of metals. Metals occur in nature in the free as well as in the combined states. The most unreactive metals, that is, which are not affected by air and water, example silver, gold and platinum, are generally found in free or native state. Most metals, however, are found in combined state in the form of their oxide ores, carbonate ores or sulfide ores, etc. The naturally occurring compounds of metals along with other impurities are known as minerals. The minerals from which metals are extracted profitably and conveniently are called as ores. Ores contain metal compounds with some of the impurities like soil, sand, rocky material, etc. These impurities are called as gangue. Metals can be extracted from the ores by employing different separation techniques. The process used for extraction of metals in their pure form from their ores is called metallurgy. Let us first understand the activity series and related metallurgy before we study the extraction of metals. You have learnt how the reactivity of elements differ for different metals. The arrangement of metals in the decreasing order of their reactivity in the form of series is called the reactivity series of the metals. Thus, the most reactive metal is potassium and is placed in the top of the list, and least reactive metal is gold, which is placed at the bottom of the list. On the basis of reactivity, we can group the metals into following three categories: metals of high reactivity, metals of medium reactivity, metals of low reactivity. Let us look at the extraction of metals of high reactivity. The metals high up in the reactivity series are very reactive, like sodium, potassium, calcium, aluminium and magnesium. These metals are obtained by electrolytic reduction. For example, sodium, magnesium and calcium are obtained by electrolysis of their molten chlorides. The metals are deposited at the cathode, which is negatively charged electrode, whereas chlorine is liberated at the anode, which is positively charged electrode. The reaction of sodium is as follows. At cathode, Na plus E minus gives Na. At anode, 2Cl minus gives Cl2 plus 2E minus. Similarly, aluminium is obtained by the electrolytic reduction of aluminium oxide. Extraction of aluminium. Symbol of aluminium is Al. Its color is silvery white. Atomic number is 13. Electronic configuration is 283 and valency is 3. Aluminium is a reactive metal and so does not occur in free state in nature. Aluminium is extracted from its main ore, bauxite, Al2O3H2O. It contains 30% to 70% Al2O3 and the remaining portion is gangue made of sand, silica, SiO2, iron oxide, Fe2O3, etc. Let us see extraction of aluminium. It involves two steps. 1. Concentration of ore, that is, conversion of bauxite into alumina by Bayer's process. 2. Electrolytic reduction of pure alumina. Step 1. Concentration of bauxite. Crude bauxite contains impurities like iron oxide, Fe2O3 and silica, SiO2. These impurities are removed by Bayer's process. In this process, the ore is first crushed and then treated with hot concentrated caustic soda, NaOH solution under high pressure for 2 to 8 hours at 140 degrees Celsius to 150 degrees Celsius in a tank called digester. Aluminium oxide, being amphoteric in nature, dissolves in aqueous sodium hydroxide to form water-soluble sodium aluminate. Al2O3 plus 2NaOH gives 2NaAlO2 plus H2O. The iron oxide in the gangue does not dissolve in aqueous sodium hydroxide and is removed by filtration. However, silica from the gangue dissolves in aqueous sodium hydroxide, forming water-soluble sodium silicate. Diluting sodium aluminate with water and then cooling to 50 degrees Celsius, it is hydrolyzed to give aluminium hydroxide as a precipitate. NaAlO2 plus 2H2O gives NaOH plus AlOH thrice. The precipitate is filtered, washed, dried and ignited at 1000 degrees Celsius to get alumina Al2O3. 2AlOH thrice, when heated at 1000 degrees Celsius, gives Al2O3 plus 3H2O. Step
The
2.
electrolyte cell is a
Electrolytic
large
reduction
steel
of
tank
alumina.
having a lining
In this
of
process,
graphite on inner
a molten
side.
mixture of pure
The graphite
alumina,
lining
whose
acts
melting
as
point
cathode.
is less than
A set
2000
of
degrees
graphite
Celsius,
rods
is
dipped
electrolyzed
in
in
a
a steel
electrolyte
tank.
act as
This
anodes.
tank is lined
On
inside
passing
with
the
carbon,
electric current,
graphite,
electrolysis
which acts
of
as
alumina
a
takes
cathode,
place.
and a set of carbon
constituent
graphite rods
elements of alumina
dipped in the
are
molten
separated at the
electrolyte
electrodes.
act as anode.
Molten aluminium is
Cryolite
used as cathode.
and fluorspar
It
is
is
also
tapped from the
added to
bottom
the
of the
mixture
cell from time
to
to
reduce
time.
the melting point
On
to
the
about
other hand,
1000
oxygen
degrees
gas
Celsius.
is liberated at the
On
anode.
passing the current,
Oxygen
aluminium
gas
is
liberated
formed
at
at the
anode
cathode.
reacts
The
with
molten
the carbon
aluminium,
anode itself
being
at
heavier
high
than the
temperature of the
electrolyte
cell
used,
and forms
sinks to the
carbon
bottom of the
dioxide
tank,
gas.
from where it
The
is removed
anodes
periodically.
thus burn away
On
during
the other
the
hand,
electrolysis of
oxygen
alumina.
is liberated at the
Therefore,
anode.
they are to be
The
replaced
electrode
from time to
reactions
time.
are shown below. At anode, 2O2 minus 4E minus gives O2. At cathode, Al3 plus 3 minus gives Al. The oxygen gas liberated reacts with carbon anode and forms carbon dioxide. As the anode gets oxidized during the electrolysis of alumina, it has to be replaced from time to time. Extraction of metals of medium reactivity. The metals in the middle of activity series, such as iron, zinc, lead, copper, etc., are moderately reactive. These are usually present as sulfides or carbonates in nature. It is easier to obtain a metal from its oxide as compared to its sulfides and carbonates. The sulfide ores are first converted into oxides by heating strongly in excess of air. This process is known as roasting. The carbonate ores are changed into oxides by heating strongly in limited air. This process is known as calcination. The chemical reaction that takes place during roasting and calcination of zinc ores is as follows. Roasting. 2ZnS plus 3O2 gives 2ZnO plus 2SO2. Calcination. ZnCO3 gives ZnO plus CO2. This zinc oxide is then reduced to zinc by using a suitable reducing agent such as carbon. ZnO plus C gives Zn plus CO. Besides using carbon to reduce metal oxides to metals, highly reactive metals like sodium, calcium, aluminium, etc. are also used as reducing agents because they can displace the metal of lower reactivity from their compounds. Example, when manganese dioxide is heated with aluminium powder, the following reaction takes place. 3MnO2 plus 4Al gives 3Mn plus 2Al2O3 plus heat. Can you identify the substances that are oxidized and reduced? MnO2 is reduced to Mn and Al is oxidized to Al2O3. The amount of heat evolved in such reactions is so large that the metals are produced in a molten state. Another example of this type of reaction is the thermal reaction in which iron oxide reacts with aluminium to give iron and aluminium oxide, evolving lot of heat. Fe2O3 plus 2Al gives 2Fe plus Al2O3 plus heat. Let us see how metals of low reactivity are extracted. The metals at the bottom of the activity series are least reactive. They are often found in free state, example, gold, silver and copper. But copper and silver are also found in combined state as their sulfide or oxide ores. For example, copper, which is found as Cu2S in nature, can be obtained from its ore by just heating in air. 2Cu2S plus 3O2 when heated gives 2Cu2O plus 2SO2. 2Cu2O plus Cu2S when heated gives 6Cu plus SO2. Similarly, cinnabar HGS is an ore of mercury. When it is heated in air, it is first converted into mercuric oxide HgO. Mercuric oxide is then reduced to mercury on further heating. 2HgS plus 3O2 when heated gives 2HgO plus 2SO2 gas is evolved. 2HgO when heated gives 2Hg plus O2. How are metals refined? Let us see. The metals produced by various reduction processes described above are not very pure. They contain impurities which should be removed to obtain pure metals. The most widely used method for refining impure metals is electrolytic refining.